I'm still I'm like, I'm not sure. It's. It's passing on my. I can get into that. There's a chat. How do you do this? What is this? Are we playing 3 and 5? Easy, but I don't do it.
Okay, some of your homework talks about one-sided limit. I haven't gone over one-sided limit explicitly, so I'll go over that today. But I can just give you a little bit of an idea. I want to highlight a couple of problems from your homework. This is 29. 29 says, use a graph to investigate the limit as x approaches c at the number c. We can use a graph, but we can also use one-sided limit. We talked about how if we're talking about if a limit exists, we're picking points on either side of our target and seeing if the arrows are headed towards the same destination. If the arrows are headed to the same destination, then we know the limit exists. The way that we represent these arrows in a more formal way is using one-sided limits. So if I have a function 2x plus 5 and 4x plus 1, and one is to the left of 2 and the other is to the right of 2, we want to know if those two graphs are headed towards the same y value as it approaches 2. So the way that we can represent those arrows using what we call one-sided limit. So if I do limit as x approaches 2, you see that exponent and that exponent negative. That indicates that we're essentially doing what this arrow is doing. We're moving towards 2 from the left side of 2. And we also want to see what is the graph doing on the right side of 2 as it heads towards 2 from the other side of 2. So from 3 to 2.5 to 2.2 to 2.1. And the way we handle the one-sided limit is we just plug in our x value into our expression, and we're going to get 9 on the left, 9 on the right. The graph, the arrows, essentially the arrows are headed towards the same y value of 9. So therefore, we can conclude that the limit as x approaches 2 of our function is equal to 9. Okay, so the homework was referencing things that I haven't gone over explicitly, and I will go over that today and tomorrow. I also want to highlight your AP practice between 6 and 8. So AP practice number 6. One-sided limits would indicate, again, we talked about how if the arrows are headed towards the same y value, if they're moving towards the same y value, that's enough for us to indicate that the limit is going to exist. So if you look at the table for 6, you see how to the left of 1, 0.7, 0.8, 0.9, the y value is holding steady at 0. It's not moving towards a certain y value. And then to the right of 0, it's holding steady at 0.9. So we don't see any movement towards any particular y value. So here we would say that the limit doesn't exist. For g of x, we see that to the left of 1, the y value is headed towards 0, right? 0.9, 0.95, negative 0.095, negative 0.009. Those are all y values that's getting closer towards zero, moving from on the negative side, right? And here, 0.995, 0.95, 0.095. These are all y values headed towards zero as well. So the left side is headed towards zero, the right side is headed towards zero. Even though that y value doesn't exist, the arrows are headed towards the same y value. So that's enough to indicate to us that the limit is approaching zero, because the limit exists because both sides are giving indication that they're moving towards the same y value. H of x, you can tell that the y value is headed towards zero from the positive side. Here, you see the y value headed towards zero on the negative side. We don't care about what's happening at that point. We care about the approach. So as long as the arrows are headed towards the same y value, that's enough for us to indicate that the limit exists. So here, the limit is existing at zero, even though the y value at that point is 1. Number 7, interpret this expression. We are essentially saying the limit as x approaches 2 for this expression is headed towards 10. So if you were to graph this function, or if you were to look at this graph from the left side of 2 and from the right side of 2, the graph is headed towards 10, moving closer towards a y value of 10 from both sides of 2. And number 8 is essentially creating what we see in this graph. If we were to use our calculator and if we were to plug in decimal values to the left of 0 and decimal values to the right of 0, we can see the behavior of the y values. The y value is headed towards 1 from both sides. If I chose x values closer and closer towards 0 on the negative side, and if I chose x values closer and closer to 0 on the other side, the y value is showing me a behavior it's consistently moving towards 1 from both sides. So therefore, the limit is equal to 1. Okay, let's continue with our notes. So I previewed one-sided limits. One-sided limit is the y value that a function is approaching as you move towards a given x value from either the left or the right side of your target x value. So example 1, the limit of x as x approaches 3 from the left side is -1. So let's say I want to look at the one-sided limit from both sides of 3. So I'm going to pick points on both sides of 3, and I'm going to move towards 3 along the path of the graph. We can tell that the arrows are not headed towards the same y value. We know the limit doesn't exist, but the one-sided limit does exist, because one-sided limit is only asking for the behavior of the arrows of the left or of the right arrow. So here, the limit as x approaches 3 from the left side of 3. So we indicate that with 3 and that exponent location. We have a negative there. Limit as x approaches 3 from the left side of 3 is equal to, what is this? Where's this arrow headed towards? What y value? -1. So the one-sided limit is -1. And then the limit as x approaches 3 from the right side of 3, to indicate that we're doing what this arrow is doing. We're starting to the right of 3 and we're moving towards 3. What is that y value headed towards? 2. So before, we had a more informal way. Yesterday, I had a more informal way of saying, okay, look, the arrows are not headed towards the same y value. The limit doesn't exist. But now we have a more formal way of saying, okay, the one-side limit, one side is headed towards -1. The other side is headed towards 2. The one-side limits are not in agreement. Therefore, the limit does not exist. You can abbreviate using D and E if you want. Okay. And the reason that the limit doesn't exist, we can say this, because the limit as x approaches 3 from the left side of 3 of f of x does not equal to the limit as x approaches 3 from the right side of 3 of f of x. So this is going to be important in the sense that this is going to be the way that you're going to justify whether a limit exists or not. Now, this is what I see some students do. I know what you mean, but this will not be able to earn you full credit. So if you say -1 doesn't equal to 2, that is true, but it's not clear enough what we're comparing, right? So we don't have to say, we don't have to specify what these values are when we justify. We just have to say that they are not equal to each other. So we don't want to write it this way. Okay. -1 doesn't equal to 2. We want to write it in this form. Sometimes I see students do it this way too, because this is the way that we say it. I understand. So we don't want to write it this way either. X approaches 3 from the left side of 3 does not equal to a limit as x approaches 3 from the right side of 3. I know that's the way that we say it, but this is an incomplete statement because we need to have something to indicate what we're talking about. Here, we're leaving something completely blank here. We need to be able to say that we're talking about the one-side limit of some function, either some expression or some function. We have to name it. We can't just write it this way. We have to indicate either the expression or the name of the function. We have to call that f of x. So I know this is the way that we say it, but this is not the way that we're going to write it. Okay, so this is also not incorrect notation. Okay, example 2, A through I. There's questions about one-side limit, about the full limit, about order pair. Let's see if we can try those, and then we can compare our answers. Yes, go ahead. Okay, check our answers. Let me know if you have any questions. Everybody okay? A through I? Okay, sample 3, a little bit more challenging here. We're taking properties and transferring it onto a graph. We want a graph that is going to fulfill all these conditions. Let's start with the easier ones first. The order pair are the easiest ones. Let's just go ahead and plot 3, -1 onto our graph. Limit as x approaches 3 is equal to 4. That means we want the graph to approach a y value of 3 from both sides of 3 towards 4. Typically, when I sketch a graph like this, I like to do this 3, 4. I like to put a hole there because I don't know what's happening at that point. And later on, I can always fill in that hole later if I realize that point is there. But as a starting point, I'm just going to put a hole there on either side. I mean, at 4, because I don't want. I don't know if there's something else that's going to tell me that the order pair is elsewhere. But I know that this is going to be the safer thing because I know I never have to erase anything. If I have to add something, I can always add that point in. But having that hole there, we're not going to have to erase anything. That is going to be the bare minimum. Okay, so that means approaching 3 from both sides is equal to 4. In fact, we do need a hole there because the order pair is living elsewhere. So I'm just going to put a hole at 3, 4, and we know the graph is going to approach from both sides. So I'm not going to extend this too far because I don't want to step on another part of the graph that hasn't been evaluated yet. So I just want to just have a hole with 2 segments extending because if I need to clean it, make it a little bit cleaner and extend it to where I want to go, I can do that later. But I know at the bare minimum that my graph this is fulfilling my condition for B. Okay, part C. The limit as x approaches -2 from the right side of -2 is equal to 1. So we want the arrow on the right side to head towards a y value of 1. So from negative, as we approach -2, a y value of 1. I'm not going to commit to that order pair, but I know my graph is going to have to extend and move towards that y value from the right side of -2. Everybody okay so far? Right. We want our graph to be increasing between -2 and 3. So looks like if I just connect these 2 lines here, I can get that to prove to be true, right? Between, oh, I'm sorry, -2, my bad. I didn't go far enough. -2, 1. Okay, so between -2 and 3, I want my graph to be increasing. So I'm just going to show that my graph is going to connect and it's going to consistently increase in y value. Okay, part E, the approach from the left side of -2, the one side limit is going to be greater than the on the other side of -2. So we know that as we approach -2 from the right side of -2, the y value is headed towards 1. We just want this side to be higher. So obviously it can't be the same. We know the limit is not going to exist at -2 because one arrow is going to head towards a higher y value than the other one. So this one you have the flexibility to choose. You can pick any point above 1, but I'm just going to arbitrarily choose a point here, and I'm just going to extend the graph. And now I'm just going to have the arrow show up on the right side, on either side. Yes.
Does it matter if it's a hole?
It doesn't matter. No, it doesn't matter. But I always like to start off with a hole because if I need to fill it in, something else in the problem will tell me to fill it in. But if you always fill it in, then you may have to do some erasing later on. So I think the safer way is to leave a hole there, and at worst, you may have to fill it in. But other than that, In this case, you can fill them one of these in and be fine. But you can't fill them both in because if you do, it'll fail the vertical line test. Okay, next page. Like we briefly talked about this with the AP practice problems, that if we are looking at a table of values, we want to look at the y values. If we see the y value is headed towards a certain specific or headed towards the same y value, then we know the limit exists, even if that ordered pair at that target is living elsewhere. So here it's easy to see limit as x approaches 3. If I pick points on either side, and if I draw arrows towards 3, that the y value is headed towards 4, right? We see that consistent movement towards 4. We can also tell this by looking at the table of values. This is describing the same thing as this, but we can also find the limit by looking at these y values. We can look at it looking at the y values here. Here, 3.9, 3.99, this is headed towards 4. 4.1, 4.01, this is also headed towards 4. We don't care what's happening at 3. The behavior of those decimals is enough for us to conclude that the limit does equal to 4. Let's skip this next one. This one's a little bit more involved than what I want us to do right now. Okay, so we know how to find limits from a graph. We know how to find limits from a table. Now, how do we find limits if we only have the algebraic expression in front of us? So the first thing we do is we just try to find the y value like I said, we're trying to plug in an x value into the function. We call this direct substitution. So this is always the first step that we do whenever we want to evaluate a limit algebraically. We just plug in the number and see what we get. Okay. So we're just going to plug -1 into all the x's and see what we get. If we get a real number, then great, that's our limit. If we don't get a real number, then we may have to go a little further, explore a little deeper into the problem. Okay, so -1 in for x. What do we get? -5. That's a real number, so that's it. That's our limit. Limit as x approaches 2 of 6. Let's think about what this graph looks like. What does y equals 6 look like? It's just a what? Straight line, right? Is that y value ever changing? No. So the limit doesn't matter if I'm approaching 2 or 3 or 6 or 8. My y value is always what? 6, right? And also, if I try to do direct substitution, there's nothing for me to plug in. There's no x for me to plug in. And so the y value is remaining as 6 at all times. So the limit is just 6. Okay, number 3. Let's always start off with direct substitution. And if we run into an issue, then we can explore further. So let's plug 0 in. What do we get when we plug 0 in? And numerator of 0. Okay, so this 0 over 0 is a form that we call indeterminate form. Now, this is not an existing value, right? This is not a real number. But visually, this does tell us something that's very helpful. Anything that is in the form of 0 over 0 visually means that there's a hole in the graph. Something that may look like this. There's a hole in the graph. It resembles some version of this graph here. So if there's a hole in the graph like this, is the limit going to exist? Yes, because even though the point may be elsewhere, though that point is undefined, if we put points on either side of that graph, the arrows are both headed towards the same y value. So whenever we see indeterminate form, we have to remind ourselves the limit exists. We just haven't found it yet. We have to explore a little bit deeper. So if you see 0 over 0, visually, that means there's a hole in the graph. Keep going. There's a real number waiting for us. We haven't found it yet. Okay, so how do we find it without the use of a graph? We're basically going to find that hole, remove it from the expression, and then reevaluate the reduced expression. So we want to find some common factors. What's the GCF from the numerator? X. Okay. If I factor in X out, I'm left with, okay, my numerator, my denominator is just an X. What can we do? Cancel out, right? And now we're basically removing the 0 over 0 out of the expression, and we're basically creating a version of the graph without the hole. And once we have the version of the graph without the hole, we can evaluate it like as if we did with number 1. So now we're going to evaluate the remaining expression, and this should lead us to a real number. So if I do direct substitution again, what do we get? -5. Okay, let's try number 4. First things first, always direct substitution. We don't know what's going on. We do direct substitution as a way of information gathering. Okay, we want to know. We don't have the graph in front of us, so we want to know what's going on. So direct substitution will give us that idea. So -7 in for x, I get 2 times 49 plus 13 times -7 minus 7. That's actually going to cancel out to be a 0. Denominator is also a 0. So we know there's a hole, but the limit exists. We can never stop here and say the limit doesn't exist. Okay, the point doesn't exist, but the limit does. We have to keep going. So the way we keep going is we can factor. There's no GCF in the numerator, but we can do trinomial factoring. So go through whichever method you're comfortable with, whether it's grouping method or star method. Okay, what do we notice? X plus 7. So we see what's causing that 0 over 0. It's the x plus 7s. We're going to remove it from the expression. Now we're going to get a version of the graph without the hole. And then if we evaluate the graph without the hole, we can find out where that limit is. Good question. Yeah. So if it was a one-sided limit, we're going to treat it like as if we're finding the true limit. Because if the true limit exists, then we know the one-sided limit will follow alongside with it. So we're going to get to that, and if not today, then tomorrow. That if we see a one-sided limit, we're going to treat it like a limit, and then if there's something that indicates that we got to do more with that one-sided limit, there will be something to tell us. But initially, we're going to pretend like it's just a regular limit, because if we can find the true limit, then one-sided limit will always be in agreement. But yeah, good question. We're going to discover that a little bit later. Okay, let's look at number 5. Any questions so far? Okay, number 5. First things first. What's always our first step? Plug in, right? We don't want to assume anything. We don't want to. I see some students, they jump into factoring and they jump through the second step before gathering information. And sometimes if you're trying to factor before you gather information, you may be starting at the wrong step. or you may be making assumptions that's not true, and that may throw you off. So always start off with your anchor step. Let's figure out what's going on. We don't want to assume anything. Okay, so if I plug -6 in, what do we get? 15/0. Now, this is different than before, right? This is not a real number, but it is also doesn't look like that 0/0. So if you see 0/0, there's a hole in the graph. If you see a 15/0, what do you think is happening? What's happening visually there on the graph? There's a vertical asymptote. These are both undefined in the sense that both these points don't exist. But if there's a hole in the graph, we know the limit is going to exist. But if there's a vertical asymptote, we know the limit does not exist. Okay. Because the graph may look something like this. Okay, I haven't really talked about infinities yet, but let's say I had a graph that looked like this. Let's say they're both headed towards infinity. Okay, so if but right now we can just stop the problem and say limit doesn't exist. But I want to talk about this a bit more. If I were to do a one-sided limit, we see that the y value is headed towards what from the left side of -6, infinity. How about from the right side of -6? Also infinity. Now, you may be looking at this going, wait, these are both headed towards infinity, so why would the limit not exist? So we say a limit exists if the one-side limits are both approaching the same real number. Okay. If it's not approaching a real number, even though if they're the same, infinity, we consider this a does not exist. So what we can say here is the limit as x approaches -6, if we have the graph in front of us, will be equal to infinity, but understand that infinity is a subcategory of does not exist. It's a way of describing in more detail why the limit doesn't exist. Visually, what's happening that's causing the limit to not exist. So if the arrows are both headed in the same direction, we can say infinity, but just understand that it's subcategory of does not exist. What if they're both headed down towards infinity? It'll be infinity, right? What if one is going up and the other is going down? Then we have no subcategory. Then the best we can say is does not exist. Okay, there are two more categories of problems where there are common factors, there are holes, but it's a little bit harder to pick out with just factoring. So we have these two additional ways of dealing with holes in the graph. One is where there's radicals involved and one where there's a complex fraction. Let's go over these steps. But we never want to assume anything. We always want to take the first step. And the first step is always what? Direct substitution. Always plug in that x value. If it's a real number, we always plug in. Okay, what do we get? 0/0. Okay. Now, I want us to, the numerator is a little bit harder to see what's going on, but we know that the culprit is that x minus 5. So basically, that 0/0 is indicating that there's an x minus 5 that's hiding in the numerator that we want to find and cancel out because denominator is very clear, right? It's x minus 5 that's causing the issue. And there's a hidden x minus 5 in the numerator. So how do we find that hidden x minus 5 where we can cancel out like before? So we call this rationalizing fractions with radicals. We're going to rationalize the numerator. Typically, in Algebra 2 and pre-calc, you may be working with rationalizing the denominator. Here, we're going to be rationalizing the numerator in the hopes that we can get an x minus 5 to show up so we can cancel out, because we know that there must be an x minus 5 hiding above. Otherwise, we wouldn't be seeing a 0/0. So we're going to be rationalizing the numerator by multiplying by the conjugate of the numerator. And the conjugate is the exact same expression as the numerator, except with a change with what? The sign of what's between the two terms, not inside the radical. You're only going to change what's between the radical and 3. So this is what we're going to do. I'm going to multiply by the conjugate of the numerator, and anything I multiply with the numerator, I need to multiply by that same expression in the denominator. Otherwise, because I ultimately want to multiply by 1. Everybody okay so far? Understanding that this is the conjugate of the numerator, and whatever you're always going to do, you're always going to copy the exact same expression above and below. We want to multiply by 1 because we don't want to change the original expression. Now we're going to FOIL and expand the numerator. But you only have to worry about the first term and last term because the middle terms will do what? Cancel out, right? So we don't have to spend the time to multiply the middle terms out. Just worry about the first and last. Okay, so first terms. What's going to happen with root x plus 4 times root x plus 4? Just x plus 4, right? Radical times radical is just the term inside that radical. And negative 3 times 3 is minus 9. Now, you're going to expand the numerator, but don't expand the denominator because the x minus 5 is already what we want to cancel out. We don't want to lose that x minus 5 into the expression. If we do that, we're going to eventually have to factor that x minus 5 out anyway. So don't do anything with the denominator. That we already want that. We already know what we want to cancel out. We don't want to lose that x minus 5. Okay, can we clean up that numerator? What does that become? X minus 5. So we know what we're looking for. We found it. We found what's causing the 0 over 0. So I'm going to cancel them out. This is what's causing that 0 over 0. Now, if I cancel everything in the numerator, there's still a what left over? A 1. Okay. So I have a reduced expression, and I now find the limit. Direct substitution, right? So any remaining x's, you're going to reevaluate. And then whatever number we get, we're hoping that we can now get a real number where before we're getting that 0 over 0. So if I replace x with 5, what do we get? Okay. Any questions so far? Yes. Yeah, go ahead. Some students have asked in the past, wait, how do I know how often I have to write out this limit? So the rule of thumb is we keep writing the limit notation until we do our final evaluation. Once we can plug in and get a real number, then we can drop that limit notation. So once I plug that 5 in and if I know I'm going to get a real number, there's no need to include that limit notation anymore. But as you're cleaning up your expression, you're going to hold on to that limit notation in front because we haven't evaluated the limit yet. Okay, number 2, first things first. Direct substitution, what do we get? 0 over 0. So we know that there is a whole. This one's a little bit strange because the radical's in the denominator, but we do know what's causing the issue in the denominator. There's a hidden x minus 10 that we don't see below. So we're going to multiply by the conjugate in the hopes that the denominator will show us an x minus 10, and we can cancel out and we can reevaluate. Okay. What's the conjugate that we want to multiply by? Okay, 3 plus, right? So we only change the sign between the 3 and the square root, but don't change what's inside the radical. All right, try that. Try those steps, and I will go through them one by one. You're going to FOIL the denominator, but you're going to leave the numerator alone. The x minus 10 is already showing showing us the factor that we want to reduce. It's the denominator that we're hoping will show us at least some version of x minus 10 to show up. Sorry. Sorry, minus. Careful here, as you FOIL out your denominator here, 3 times 3 is 9. That's fine, right? What's going to happen when I multiply square root and square root? X minus 1. What happens though when I multiply by a negative times a positive? Negative. What's going to happen with that negative? I got to deal with that negative. Distributed, right? So we got to be careful about that. We need to have a set of parentheses after we drop the radical. We have to remind ourselves that the negative is going to have to distribute through. So that's a little bit hidden, right? We've got to just be careful about that. Nine minus x minus 1, this becomes 9 minus x plus 1, which is 10 minus x. Now, these are not exact perfect matches, but they're pretty close. Is there anything that we can do to get these to match up? Yeah, either I factor a negative 1 from the denominator or from the numerator. Either way, I know that these are only off by a factor of negative 1. So however way you want to do it, we can just cancel them out and know that there's a negative 1 left over. That's fine as well. Reevaluate, and we should be able to get down to a real number. Okay, I'm running out of time here. Try your best with the homework. I didn't get a chance to get to complex fractions. I'll do that tomorrow. I'll also have help sessions in the morning tomorrow, 7:45. All right, come get your phones, guys.
Look at the note. Because we shouldn't have.
Then I actually walk into it.
I'll say a long.
But I didn't believe it. I'm like, yeah. I got stuck in from Joe. So senior to go. I'm told. Yeah, I got caught. Very